Welcome back, dear all, in our next session. In this session, we are going to learn a numerical on displacement time, velocity time, acceleration time, and jerk time graph for the follower moving with uniform acceleration and retardation motion, that is UARM. So, our question is a cam with minimum radius of 50 mm rotating clockwise at uniform speed. So, is required to give a knife edge follower the motion described below. To move outward through 40 mm during 100 degrees of rotation of cam. So 40 mm is the displacement of the follower and 100-degree rotation of the cam. So during 100-degree rotation of the cam is moving, the follower is moving in the outward direction. That means it is the angle of outstroke. To dwell for next 80 degrees, so 80 degrees is dwell. To return to its starting position during next 90 degrees, so 90 degrees is the angle of return stroke, and to dwell for the rest period of revolution. So next part is remaining part is the dwell. So the displacement of the follower takes place with uniform acceleration and retardation motion, that is UARM. Determine the maximum velocity acceleration of the follower when the camshaft rotated at 900 rpm. So 900 rpm is the angular speed of the cam or angular speed of the camshaft. Draw the displacement, velocity, acceleration and jerk diagrams for one revolution of the cam. So it is the question on uniform acceleration and retardation motion of the follower, which is in contact with a cam rotating with certain we're rotating through 100 degrees during outer stroke, 80 degrees during dwell, and 90 degree during return stroke, and the remaining part is dwell. So let's start solving the question. So displacement of the follower is given as 40 mm, outstroke angle is 100 degrees, then first dwell is 80 degrees, then return stroke angle is 90 degrees, and the speed is 900 rpm. Now one more thing, so you can calculate the angular velocity over here. Angular velocity formula is 2 pi n upon 60 and is given 900 rpm. So put the value of n and you will get angular velocity in radians per second. I suggest one more thing here you can do is this theta O, that is angle turn during outstroke, is given in terms of degrees, that is 100 degrees. So you can calculate it in terms of radians multiplied by pi by 180 and you will get outstroke angle in radians. Similarly, you can calculate theta R, that is 90 degrees, in terms of radians. So multiplied by pi by 180 you will get the theta R in terms of radians. That may be useful in the further calculation part, we will see later on. So the displacement of the follower, as we had seen in our earlier lecture, how to plot the displacement diagram of the follower moving with uniform acceleration and retardation motion. So this is 100 degrees during 100 degrees of cam rotation. The displacement of the follower is 40 mm. Next 80 degrees is dwell, and next 90 degree is return stroke. So this is the displacement of the follower during outstroke, during dwell part, and during return stroke. The remaining part is dwell, so that need not to be shown over here. So that's how we are going to plot the displacement graph. If you want a step-by-step guide how to plot the displacement diagram for a follower moving with uniform acceleration and retardation motion, you can see my earlier video. So velocity during outstroke, the formula for velocity during outstroke is 4s omega upon theta O square into theta. So this s is the displacement, omega is the angular velocity we had found out, s is already given, theta O, that is angle turn during outstroke, it is also given, theta is the only variable. So we have to calculate velocity at three positions: at the start, at the middle of outstroke, and at the end of outstroke. So let's start calculating. Now at the start of outstroke, when angle turned is 0, So if you put the 0 over here, this entire term will become 0 and the velocity at the start of outstroke will become 0. Now at the half of outstroke, so at the half of outstroke, that means when theta is equal to theta O by 2. So if we put theta O by 2 over here, so theta O and theta O square will get cancelled. So what will remain is 2s omega upon theta O, 2s omega upon theta O. So we'll put all the values over here. Velocity at theta O by 2, so 2s omega upon theta O. So put all the values. 2s omega upon theta O. As I had said you earlier, if you found theta in terms of radians, so instead of putting this value 100, that is 100 in terms of degrees, into pi by 180, so to convert it into radians, if you calculate it earlier, then you directly need to put the value of theta O in terms of radians. So some step will get reduced, so you can do in both ways. So that comes as 4319.64 mm per second. Let's convert it into meter per second. Multiply it by 10 raised to minus 3. You will get 4.3 meters per second. That is the velocity at the half of outstroke. Now at the end of outstroke. So at the end of outstroke means when theta is equal to theta O. So if you put theta O instead of theta over here, so you will get some constant value over here. But we know that at the end of outstroke, the velocity, the follower comes back to at rest. As the follower comes back at rest, its velocity must be 0 at the end of outstroke. So instead of putting the value over here, we will put directly the velocity of the follower at the end of outstroke is 0. So that's highlighted over here. Velocity at the end of outstroke, it should be 0 instead of some constant value. Now let's go for return stroke. As during outstroke, the velocity of the follower is 4s omega upon theta O square into theta. So the same formula will be there, but only difference is instead of theta O, we have to put theta R over here. And as the velocity during outstroke we are taking as positive, so during return stroke it should be taken as negative, because velocity is a vector quantity and positive and negative sign indicates their directions. So direction of velocity, as it is moving down, the follower is moving downward, that's why its velocity will be considered as negative. Minus sign only indicates its direction. So velocity at the start of outstroke, so you put means at the start of outstroke means theta R equal to 0. So if you put theta equal to 0, so if you put 0 over here, you will get the entire term as 0. So velocity at the start of outstroke is return stroke is 0. Now velocity at the half of outstroke. So at the half of outstroke means when theta is equal to theta R by 2. So instead of theta, you have to put over here theta R by 2. So you will get minus 2s omega upon theta R. Minus 2s omega upon theta R. That formula you will get. Put all the values over here. So theta R you can put in terms of radians directly over here, or you have to multiply it by pi by 180 when you put in terms of degrees. So we had put here in terms of degrees, so multiply by pi by 180. This entire term is theta R only. If you calculate it earlier at the start, then you have to put the value of theta in terms of radians directly instead of multiplying by pi by 180. So minus 2s omega upon theta R. So its value comes as 4802.03 mm per second with minus sign. So convert it into meter per second, so it is minus 4.8 meters per second. Again, velocity at the end of return stroke, it must be 0, as we had seen earlier during outstroke, so it must be 0 over here. So let's plot it. As we know how to plot the velocity diagram for a follower moving with uniform acceleration and retardation motion. So during outstroke, the velocity at the start is 0, at the end is 0, at the half of outstroke it is 4.3. so by taking suitable scale in vertical direction, it is 4.3 meter per second. So during return stroke, velocity at the start and at the end of return stroke it is 0. At the half of return stroke it is 4.8, meter per second. So this 4.8, it must be greater than 4.3. So you have to choose a suitable scale in y direction. In y direction there is velocity, in on x-axis there is angle turn, and on y-axis there is velocity. So we have to plot the velocity, and as we know that it is uniform acceleration and retardation motion. That means rate of change of velocity per unit time is constant. That's why velocity rise is constant over here. That's why we have to represent it by straight line. So during half of our stroke, its slope is continuously positive, so it is straight line. And again during next half of our stroke, it is again a straight line. So we have to represent the velocity with the help of a straight line in case of uniform acceleration and retardation motion, as we had seen in our earlier video. So similarly, during the return stroke, the velocity is represented by a straight line because its slope is constant or acceleration is constant. When acceleration is constant, then slope is constant, and if slope is constant, then that means the lines are straight inclined lines. That's why the velocity is represented by straight inclined lines in the velocity diagram. So acceleration is constant, as we had seen earlier. During out stroke, it will be taken as plus or minus 4s omega square upon theta o square. So as it is a constant, means from the start till the end the acceleration will be constant, that is plus minus 4s omega square upon theta o square. But you can observe from this diagram that during first half of our stroke the slope is positive. That means during first half the acceleration is positive. During the next half of our stroke, as its slope is negative during in the velocity diagram, that means acceleration is negative during the next second half of our stroke. That's why the acceleration have same constant value, but it is negative acceleration or retardation or deceleration. Similarly, during the return stroke, during the first half of return stroke, here in this is the line representing the velocity. That means its slope is negative. If its slope is negative, that means at the start of return stroke, during first half the acceleration is negative, or it is retardation or deceleration. During next half of return stroke, the slope of this velocity diagram is positive. That means the acceleration is positive during the second half of return stroke. So during out stroke, the acceleration has certain constant value which is positive in the first half, negative in the second half. Similarly, during the return stroke, the acceleration has certain constant value which is negative in the first half and positive in the second half. Its value will be constant, but it is plus minus in out stroke and minus plus in return stroke. So it is plus minus over here. Put all the values as a constant. So for s is 40 mm, omega we had calculated 94.24, and theta o is 100 degrees. Let's convert it into radians. So multiply by pi by 180. If you had calculated theta o in radians earlier, so directly put the value of theta o in radians over here. You need not to put this entire calculation over here. So put all the values and you will get the acceleration, that is plus minus 467.43 into 10 raised to 3 mm per second square. Let's convert it into meter per second square. So it is 467.43 meter per second square. It is not mm, I'm sorry, there is some typing mistake over here. It is meter per second square. Now acceleration during return stroke, it is, as we had seen, as discussed earlier, it should be minus plus 4s omega square upon theta r square. During out stroke it is theta o, during return stroke it is theta r. During out stroke it is plus minus, during return stroke it is minus plus. Put all the values over here. So for s is 40 mm, omega 94.24, theta r is 90 degrees, and to convert it into radians, multiplied by pi by 180 and its whole square. So the acceleration during return stroke comes as minus plus 576.48 into 10 raised to 3 mm per second square. Let's convert it into meter per second square. So minus plus 576.48 meter per second square. So let's plot the acceleration diagram during outstroke and return stroke for the follower moving with uniform acceleration and retardation motion. So during first half, as we had seen earlier, it is positive as the slope here in the velocity diagram is positive, so acceleration is positive during the first half. During second half, it is negative as its slope is negative in the velocity diagram, so here the retardation or deceleration, it is negative over here. Similarly, during the first half of return stroke, the slope is negative, that's why it is minus acceleration, negative acceleration or retardation. And during the second half of return stroke, the slope is positive in the velocity diagram, that means acceleration is positive, so it is positive over here. So we have to, if you want in detail plotting how to plot the displacement diagram, velocity diagram or acceleration diagram, you can see my earlier video of plotting of displacement, velocity, acceleration and jerk diagram for the follower moving with uniform acceleration and retardation motion. I had posted earlier on the YouTube. So this is the acceleration part. Now next part is jerk. Now jerk of particle moving with uniform acceleration and retardation motion. As we know, jerk is rate of change of acceleration with respect to time, or it is differentiation of acceleration with respect to time. As the acceleration is constant, so it is not changing, that means the acceleration is constant, and differentiation of acceleration with respect to time will lead to 0. So jerk must be 0 while the follower is moving with UARM. So all the values are constant over here. If you differentiate it, you will get the 0 value at the jerk, for the jerk. But there is some issue over here. It should be 0 theoretically, the jerk should be 0 theoretically, but practically there is some amount of jerk present, we see later on. So as we are seeing a vertical line over here, that means at the start of outstroke, when the acceleration was 0 and suddenly it reaches certain constant value of acceleration at the start of outstroke, so it is a vertical line. And as we had seen that jerk is differentiation of acceleration, or jerk is the slope of acceleration graphs. Jerk graph is slope of acceleration graph. So as this is the acceleration graph, here it is horizontal line, so its slope will be 0, so jerk will be 0 over here. Here again it is horizontal line, so its slope of horizontal line is 0, that's why jerk will be 0 during the second half of outstroke. But at the start of outstroke, here there is a vertical line. Now slope of vertical line is always infinity, so at the start of outstroke acceleration is 0 and suddenly it reaches certain constant value of 467.43 meter per second square within no time. That means infinite amount of jerk is required at the start of outstroke to achieve this amount of constant acceleration. As this amount of constant acceleration requires infinite amount of jerk, so at the start of outstroke there is infinite jerk we have to show over here. Similarly, during at the half of outstroke, the acceleration was certain positive and suddenly it reaches certain constant negative value or retardation value, so it is represented by a vertical line. As the slope of vertical line is infinity, that's why infinite amount of jerk is required at the half of outstroke to achieve certain amount of negative constant acceleration from certain amount of positive constant acceleration. So infinite amount of jerk in downward direction is required at the half of outstroke. Similarly, at the end of outstroke, as there is a vertical line over here in the upward direction, that's why infinite amount of upward jerk is required to achieve this negative acceleration to 0 acceleration value at the end of outstroke. Similarly, at the start of return stroke, as this is a vertical line, its slope is infinity, so infinite amount of jerk is required to achieve certain amount of constant retardation value, that is 576.48 in negative direction. So infinite amount of jerk is required at the start of return stroke. Similarly, at the half of return stroke, infinite amount of jerk is required to achieve certain amount of constant acceleration from certain amount of constant retardation within no time is achieved. So it is represented by vertical line, and as the vertical line slope is infinity, so it requires infinite amount of jerk in upward direction. Similarly, at the end of return stroke, the infinite amount of jerk is required to achieve zero acceleration at the end of return stroke. So that's how we can plot the displacement, velocity, acceleration and jerk diagram for the follower moving with uniform acceleration and retardation motion. This is the complete plotting. You can plot it on the graph paper or a simple plain paper or on a sheet, that is half imperial sheet or a quarter imperial sheet. You can plot these graphs. This is called as displacement diagram, this is velocity diagram, this is acceleration diagram, and this is jerk diagram. On the y-axis, here there is displacement, here there is velocity on the y-axis, here there is acceleration on y-axis, and here there is jerk on y-axis. So here we complete this numerical on follower moving with uniform acceleration and retardation motion. Thank you. Let's see in our next lecture on the displacement of follower moving with simple harmonic motion. Thank you.